Hey guys, in this video I will discuss another method of finding the volume of a solid of revolution. This method is called the method of cylindrical shells. So let's get started. So here we let F to be continuous and non-negative on AB and let R be the region bounded above by y equals f of x, below by the x-axis, and on the sides by the lines x equals a and x equals b. We want to find the volume of the solid of revolution that is generated by revolving the region about the y-axis. So in here, we have this region, and our axis of revolution is the y-axis. Okay, so if we revolve this, we will be able to create this solid here, the gray area. And notice that in here we have a hollow, but doesn't matter. So what is this method of cylindrical shells? First, let us define what a cylindrical shell is. The cylindrical shell, it's a solid enclosed by two concentric right circular cylinders. So in here, I have a cylinder here, smaller one, and I have another cylinder here, a bigger one, which has the same center as the smaller circular cylinder. Now, the cylindrical shell is the solid in between those two cylindrical or cylinders. So basically, this one here will be, it could be a hollow. Okay, so here we have the solid part. Now, if we want to find the volume of this cylindrical shell, given that the height of our cylindrical shell is h, the outer radius equals r sub 2, and the inner radius is equal to r sub 1. So the outer radius, that's from the center of your cylinders, okay, going to the outer surface of your shell, and the inner radius, that's from the center of your cylinder to the inner surface of your shell. So you can see R1 is less than R2. Anyway, in order to find the volume of this cylindrical shell, well, the volume is just get the volume of the big cylinder, subtract the volume of the smaller cylinder. So in here, we have pi r2 squared h minus pi r1 squared h. The volume of the bigger cylinder is pi r2 squared h, and the volume of the smaller cylinder is pi r1 squared h. We just factored out h in here. Now, we can also factor out pi, that's what you see in here, and you will be left with a difference of two squares, r2 squared minus r1 squared. So if we factor that difference of two squares, we will get this product, r1 plus r2 times r2 minus r1. Take note, r2 is bigger than r1 in here. What we're gonna do is to multiply and divide by 2. So this step here is necessary in order for us to have a nice choice for our derivation of the volume. Of course, R2 minus R1, that's your change in radius. H is your height. The change in radius, if you look at this, it's basically the thickness of your cylindrical shell. This one here is R2 minus R1. So if you look at this, that is our thickness. Here, you got R1 plus R2 divided by 2. But that's just a formula of average given two numbers. A and B, the average is just the sum divided by 2. What's important in this part here is that, in general, if you got two numbers A, B, and you get the average is actually somewhere in the middle of your two numbers. It's the average, so it must be in the middle, the exact midpoint of the two numbers. So we interpret that as average radius. All in all, the volume is equal to 2 pi times the average radius times the height times the thickness. So how are we going to use this formula for our volume problem? Remember that we got this function y equals f of x, and then we revolve it about the y-axis. And this gray part here, or throughout, that will be the solid part, or that's actually the solid of revolution. Now, if you look at this, there are stripes. These stripes here represent your strips, vertical strips in this case. If you revolve, for example, this R2, capital R2, if you revolve this about the y-axis, it creates a cylindrical shell. This gray part here, this strip here, if you revolve this about the y-axis, it creates another cylindrical shell. So in order to find the volume of the solid, we need to find the volume of each cylindrical shells and then add them together. Okay? Now, let us complete the derivation. So, if you get one cylindrical shell here, it will look something like this one. The cylindrical shell, the thickness, will be represented by delta x sub k. If this is your kth subinterval, x sub k minus 1, x sub k, the average here will be the sum of these two numbers divided by 2. And it is always in the middle. So we can choose that as our sample point, x sub k star. Choosing this x sub k star as our sample point, we evaluate it in the function. Take note, let me go back. This is our function. The top part here, that's your function. Which means the height is from this part of the function going to, well, the bottom. In our case, that's our x-axis here. So as you can see in this one, the height of our cylindrical shell is f of x sub k. So, the details, we divide the interval AB into n subintervals. In our computation, n subintervals of equal length, so we'll just denote it as delta x. I mean the length of the subinterval is delta x. For the kth subinterval, we choose the midpoint. That will be our sample point. So very specific sample point. In the derivation, in the definition of definite integral, it only says choose any sample point. Any sample point will work. But for our cylindrical shells method, we choose a specific sample point. So after choosing that, The height of the slab, this cylindrical shell here, will be f of x sub k star, and the thickness is delta x. The average radius is x sub k star. So in here, we got the 2 pi. This one here, it's the av radius. This one here is the height. And this one here, that's your thickness. That will be the volume of that particular shell. And of course, you do this to all subinterval. The volume will be approximated by summing those V sub k here, the volume of the kth slab or the volume of the kth shell. And of course, if this expression here is integrable, then the volume will be the integral from a to b of 2 pi x f of x dx. So take note, this x sub k star corresponds to this x. And as you can see, f of x sub k star, that becomes your f of x. Okay? Now, what I want you to remember is that the volume, this is equal to, of course, integral whatever, a to b, 2 pi. Then you got here the av radius. Take note that the average radius is basically the x here going to the center of the shell, which is the axis of revolution. Okay? That will be your average radius. And then here, you will have your height, which is basically the function, and then your thickness, which is your dx. So average radius and height. Those are the two things that you need to identify when using this method of cylindrical shells. Similarly, if we have the y case, this time you have your function. Say this is your function, y equals, it's x equals g of y. And then this is your c, this is your d, c, d. This is the region. The axis of revolution is here. Horizontal axis of revolution, your strips are here. Okay? In the vertical case, your strips are vertical. Let me show. The strips here are vertical. The axis of revolution is vertical. The strips are vertical. So the variable, since the strips are vertical, the variable that we're going to use is the variable x. On the other one, the axis of revolution is horizontal. In this method, the strips are also horizontal. Since the strips are horizontal, the variable that we will use is the variable y. Okay? So, again, let me just have a quick summary here. Washers, or let's see, we have disc, washer, you will know axis of revolution, axis of revolution perpendicular to strips. Cylindrical shells axis of revolution axis of revolution parallel to the strips. Okay? Disc or washer, axis of revolution perpendicular to strips. Cylindrical shells, axis of revolution parallel to strips. Talking about the strips, vertical, X. This is your variable. Horizontal strips, the variable will be Y. So it is the orientation of the strips that dictate which variable to use. It is the orientation of the strips that dictate which variable to use. The orientation of both axis of revolution and strips dictate which method to use. You will see later that if that sometimes when you use your disc or washer, the integral is not easy to do. You can solve the same solid using a cylindrical shell. Your axis of revolution is fixed. It is the strips that you're going to change, the orientation of the strips that you're going to change. Hence, the variable to use. Okay? So, let us consider this one. Use cylindrical shells to find the volume of the solid generated when the region enclosed by y equals square root of x, y equals 2, and x equals 0 is revolved about the y-axis. This problem, we already did this one in our previous video. So in here, you got y equals square root of x, so you have this, y equals square root of x, y equals 2, of course this will become 4. So this is y equals 2, and the y-axis, so the region will be this part here. The axis of revolution is the y-axis as well. Y-axis. In the previous solution, we use this one here. Okay? And then we use disk because when you revolve this, you will have a disk. This time, it is specified that we need to use the cylindrical shells. The axis of revolution is your y-axis. In the cylindrical shells, the strips must be parallel to the axis of revolution, which means if the axis of revolution is vertical, the strips must also be vertical. This strip will go from the left to the right. The leftmost value of x will be 0, the rightmost value of y will be 4. And notice that as you move the strip, this upper portion will always be the y equals 2. This lower portion will always be the function y equals square root of x. We are using vertical strip, so the variable will be in terms of x. So, since the axis of revolution is the y-axis here, we just have the average. The average radius will be x. So, av radius is equal to x. What will be the height of this strip? The height is from here, which is y equals 2, going to this point, which is your y equals square root of x. So I hope by this time you have identified, or you already know how to get the radius or the height if if one of the endpoints is not your x-axis or your y-axis. So in here, the height will be 2 minus square root of x. Therefore, the volume will be equal to integral from 0 to 4 2 pi times the average radius, which is x, times the height, 2 minus square root of x dx. So this will be the volume of the solid generated. Take note that in the previous video, this is the same solid as in one of the examples before, but the method that we used there was method of disk. Since we are getting the volume of the same solid, the volume that you should have obtained in the previous example, in the previous video, must be the same as this volume. So try to compare their final answers. Okay, let us have another example here. Use cylindrical shells to find the volume of the solid generated when the region between the curve y equals x squared and the x-axis over the interval 0, 2 is rotated about the y-axis, line x equals -1 and line x equals 3. So if you would remember, this problem was the same or similar to the last problem in the last video. Y-axis, x equals -1 and x equals 3. But this time, we'll be doing a different method. So let us consider the three scenarios. We have y equals x squared, something like this. And then the x-axis over the interval 0, 2. So let us have this one here, 0, 2. So this will be the region. And let me copy this again. Let me copy. So that's what we're going to use for the first letter. This is for the second letter here. And then we got the third letter. So for the first letter, we want to find the volume when the region is rotated about the y-axis. So this one here. Method of cylindrical shells. So Vertical axis, vertical strip. If we try to revolve this, okay, let's just get the shell. If we try to revolve this, it will be something like this. And then there is the shell somewhere here. Okay? The height is just from the function going to the lowest point here, which is your x-axis. So height equals x squared. The average radius is when you pick an x here, what is its distance from the axis of revolution? That will be your av radius. So in here, the av radius will be simply x, which means volume equals the integral. The strips will run from 0 to 2, and we have 2 pi, average radius, height, which is x squared, and then the dx. Okay? For letter B, the axis of revolution is at x equals -1. So this is our x equals -1. The strips, since the axis is vertical, the strip is also vertical. The height of this is still x squared. Height, this is still x squared. But the radius will be different. The average radius will be different. If you choose your x to be here, the average radius should be from x going to this one here. X is up to this point only. This is your x. From this point going to this point, that's equal to 1 unit. Which means the average radius here, radius, this is equal to x plus, I'll write it as x minus 1. Or you write it as x plus 1. Which means the volume will be the integral from 0 to 2 times 2 pi times the average radius is x plus 1 times the height, which is x squared, and then we have the dx. For the third letter, the axis of revolution is x equals 3. Again, it's vertical, so we use vertical strips. The height will remain as x squared. But what will be the average radius? The average radius is, you get the x, that's the midpoint of that sub-interval, going to the axis of revolution. That's your average radius. Take note that when you revolve this about the line x equals 3, your shells will be something like this. Correct? So it's on the other side. So the radius is from here going to that, or here going to that. But what is this length here? Well, x equals 3 is from this one up to this point. This is x, which is from this point up to this point. So this length here is 3 minus x, which gives us the volume integral from 0 to 2 pi times 3 minus x times x squared dx. So you can try to solve for each definite integral here and then compare it to the answers in the previous lecture. Take note that you will generate the same solids, so you should have the same answers. Okay? One last example. Actually, yeah, let's have this second to the last example. Use cylindrical shells to find the volume of the solid generated when the region between the graphs of the equation f of x equals 1/2 plus x squared and g of x equals x over the interval 0, 2 is revolved about the x-axis. So in here, I hope you remember this. This is actually one of the examples that we did in the previous lecture. Here you will have your y equals g of x equals x, and then we have the parabola 1/2 x squared, and then we have this region here from 0 to 2, 0 to 2. The region will be this one here. Now, when we did this, the axis of revolution is about the x-axis. When we did this using the method of washers, we use vertical strips because we must have a perpendicularity for with the axis of revolution, I mean. But since now we are going to use cylindrical shells, the strips we're going to use must be horizontal. Now, if you look at this, you will have to run from the lowest point going to the highest point here. The highest point here is what? X equals 2. So 2 squared, that's 4 plus 1/2. The highest value of y here is 4 plus 1/2. So that will be equal to 9/2. But let us check. Here, we will divide this into 3 parts. If we use cylindrical shells, you will be required to divide this into 3 parts. The reason is, if you move this rectangular strip from lowest point to the highest point, this rightmost part and the leftmost part will change at some point. What I'm saying is, if we consider this up to this point only, the leftmost part is this segment here, which is x equals 0. The rightmost is this line. So you will have this portion. But beyond this point, you will get these strips. The leftmost is this part here. It's now the parabola. The rightmost is still this line. So you will get this portion here. Okay? So from here, going here, and then going here. So there is a change in the leftmost. But beyond this, you will have this set of strips. The leftmost is still the parabola, but the rightmost is now this vertical line. So apparently, if we use cylindrical shells here, then it becomes more complicated. So it will be nicer to use the method of washers or method of this in this case. Conversely, there will be times that when you use your method of this or method of washer, it is more complicated than using the method of cylindrical shells. So if you are not forced to use a certain method, decide which one is faster to do. It will be up to you. Okay? So anyway, try to set up the volume, the definite integrals that will give the volume of the solid that will be generated. One last example for this topic. Again, use cylindrical shells. The region is under the curve y equals x squared. Y equals x squared over the interval 0, comma 2. So this is 0, comma 2. So this is our region. And then we got two cases here. Rotate about line y equals -1, and then the other one is rotate about line y equals 5. So let me copy this part here. Copy, paste. So for the first one, line y equals -1, so we will have this axis of revolution. Y equals -1. Cylindrical shells, so we have to use horizontal strips because, well, the axis of revolution is horizontal. What is the height? So if we revolve this, you will have this shell here. We'll have this shell here. Then we have that part there. Okay? The height will be from this point going to this point. Take note that we are doing horizontal strips. So we have to change this because the variable should be x in terms of y. So this will be x equals square root of y. Take note that we are only considering the interval 0, comma 2. So the values of x are positive only. That's why we only have this square root of y. If we were considering a negative interval, then you will need negative square root of y as well. So anyway, what is the height? The height will be from this point going to this point. This point is x equals 2. This point is, well, x equals square root of y. So the height will be 2 minus square root of y. So again, x equals 2 This one here is x equals square root of y. So from this point going to this point, that's our height. What about the average radius? We choose a y. Take note, since horizontal strip, the midpoint is a y value. So this is y. And what is this? Its distance from the center. Well, this part here is y. This here is 1 unit. So it becomes y plus 1 unit. Or I will write it as y minus negative 1. So this one here is y plus 1. Y is this part here. This one here is 1 unit. Therefore, volume equals the integral. Lowest point is 0. Highest point here, this is 4. So 0 to 4, 2 pi. Average radius is y plus 1. Height is 2 minus square root of y. Then we have the dy. Sorry, 0 to 4 here. That will be for letter A. For letter B, this is y equals 4, but you are revolving about the line y equals 5. This is y equals 5. Cylindrical shells, we have a horizontal axis of revolution, so our strip will be horizontal as well. Height is still the same as in the previous one. It's still from this point up to this point, so it won't change. It's 2 minus square root of y. The average radius, you will choose this as your y, but the average radius is from the axis of revolution, which is up here, going to that y here. So if you look at that, from here up to here, from this up to this is 5 units. From this up to this is y units. So this part here will be 5 minus y. So the average radius will be 5 minus y. The strips will still run from 0 up to 4. So the volume will be the integral from 0 up to 4, 2 pi times the average radius, 5 minus y, times the height, 2 minus square root of y, and then the thickness, dy. Right? So, that will be the end for this video. And please study this new method and try to compare the answers using this method with the answers using the method of this or washer. Okay? And then you will be able to at least recognize which method is more faster to do than the other one on a case-to-case basis. Take note of that, case-to-case basis. Okay? So, thank you.